Okay, hello guys, nice to meet you again. Okay, today we'll continue our physical lectures, Spaces and Times number 3. And today, okay, first of all I want to ask, how was the previous examples, questions? Are we okay? Did you manage to do something?
Yeah.
Okay, I will continue it. I hope you're okay. Okay, so today we'll talk about principles of relativity. Principles of relativity. The principle of relativity we mentioned a little last time. First was pointed out by Galileo Galilei, remember? It was in 1632 or something. And it was the first, like officially, the first principle of relativity. So we'll talk, actually there are lots of principles of relativity because they were generalizing, they were making them more applicable to many things around. They were step by step, so many years from there. And actually now principle of relativity, whatever you call it, or any of these principles, or the main principle of relativity, is actually the main concept in physics. Right now it's like fundamentally main, the first, the beginning of all physics. You can talk it like this, you can say like this. So it's very important, so we have to understand that. We will talk about it later many times more, touch this and this from this and that side, but today we'll talk like in general about all these type of principles. So the first principle of relativity found out by Galileo Galilei in 1632, around this time. It was, I will remind you, it was about systems of reference. And system of reference actually it's sort of a physical understanding of point of view. So anything can be point of frame of reference, like moving train. If you are on this train or you're looking in the world from this train, this is your frame of reference. If you're in the rocket, a rocket is the frame of reference. But also frame of reference includes many other things, like the clock. If you have a clock and you're counting time on your rocket or maybe boat or whatever, so again this clock is your part of your frame of reference. Also, any person can be frame of reference from his point of view, and because each of us have their internal, like biological clock inside our brain. So we have our clocks, we have our measuring devices, because we can estimate like what's the distance from me to the next wall or something like this, or maybe know how many distance like from here to Boston, for example, like 45 miles or something like this. So we have these measurement devices, our meters, or maybe some other system of clocks, the devices on the car which measure the mileage that when we're riding on the car, and lots of other things. Actually, frame of reference can include many things, including like any measuring things, like registering something, like for example charge of some particle, or maybe the smell, or whatever. Lots of physical features. That's all may be included into frame of reference, and then it becomes a device, experimental device, or even a human as a whole thing, in addition with some devices which we use as humans, right? So, and this principle of relativity was about so-called inertial frames. So inertial frames are the frames or systems like that are moving without changing their speed, or as Isaac Newton would say, inertial system. So it goes like by inertia, goes far in the space, moving in space, straight forward somewhere infinitely. So inertial frames of reference. And in inertial frame of reference, if you talk about this and think about it, it comes to the thing which is called addition or subtraction of velocities. So for example, if we have a person, like who is moving this way, step by step, with certain speed, right? Like maybe 1 step per second, for example. So we have this velocity or speed of this man, right? And how we measure this velocity? We measure it from our own frame, which is like us standing beside, not moving. We're standing and looking at this person. So our frame of reference is ourselves. This is our frame of reference. Or device, whatever, measuring device. And we look at the guy moving. So what we see? Moving step by step, like 1 step per second, for example. Now, let's do something with this frame of reference. Let's let's follow this person with the same speed. So this person makes 1 step, we makes 1 step, right? The same velocity. What will be the relative speed of this person to us? What do you think?
Like V2? I'm at 2V.
Okay, he's going this way. We are following him, the same speed.
Oh wait, it would look like he's not moving because we're just looking at him.
Yeah, the distance is not changing, remember? Because we are following him exactly, straight, right? So in this case, if we put it like V and V, the relative speed, VR, we may say, right? VR obviously will be 0, right? And this is actually, it may be derived from this principle that Galileo Galilei put, so it's pretty easy to understand. Like now let's look about how it will be for another frame. Like we're going not following the person, but we're going just opposite direction with the same speed. What will be relative speed? What do you think?
Now
So here he makes 1 step there, we make 1 step here. So the distance increase how many steps? 2. So 2 steps per second, right? So the relative speed will be V plus V, 2V, right? So in the first case V relative was 0, right? So it was V minus V equals 0. And the second frame of reference, you see the man is still going, this man, the first man, right? But we are changing our frame of reference. So we're just looking from different points of view. So from one point of view it was 0, from another it was 2V.
Huh? Isn't there one more where they're moving towards each other?
Yes, that is the third, right?
Okay.
The third will be moving towards each other, okay? So this way, and this, he is moving this way too, right? Or maybe it's not that. He is moving the same way, right? V, right? But we change our frame of reference to here. We move here, right? And we move this direction with the same speed. So, and this will be our relative speed. So what speed would it be relative? What do you think?
We said they're moving towards each other. Each moving at speed V.
Guys.
Oh, minus 2V? Sorry. Data minus 2V.
Yeah, something like this. Yeah. So it's still 2V, but definitely opposite direction, right? And that in the second thing we are moving from each other, right? It's what increasing, and when something increasing, it's maybe taken as plus, but it's relative. It can be taken as plus. If we took it as plus 2V, right? So the third, you are totally correct. It will be minus V and minus V actually. Will be minus 2V. In both cases, actually, you see the speeds are adding to each other. Just here is taken like minus sign, and here is taken a plus sign. But they are added here and added here, right? You see, right? Just here we add plus V and plus V. Here we add minus V and minus V, and we get minus 2V. So it's the same thing, but a little different frame, a little different approach. So, but anything what we see here, it is called the principle of adding the speeds, or calculating of relative speed. Frame of reference and something that we measure the speed of, right? And remember, the same thing was, it's not the third case, but it's actually the first case. First, maybe prime, right? First case prime. If we are in the car, right? The car is moving with the speed v, and inside car, the person is moving with the speed v too. The same speed. So he is moving with the speed of the car. He's not walking in the car. He's actually standing. But he is moving with the same speed, right? Because he's standing in the car. So the relative speed will be? Zero, right? So the same case. So VR prime, right, will be again 0. It's pretty easy. So in this case, remember, we talk about this, right? So we're in the boat and moving straight without any acceleration, no changes in speed and everything. So we have this thing. So this is all actually about this first principle of relativity of Galileo, Galilei, right? Now, it was in 1632. Now let's talk next principle. In 300 and something, 300, almost 30 years later, in 1905, there came another guy whose name was Albert Einstein, who started thinking of this principle of relativity 300 years later, right? Why should you think about it? Like, this principle was very good for 300 years. Everybody used it. Yes? Pardon me?
Because you can add or change to it.
You can what?
Because you can add or change to what was already made.
Yes, but what kind of change? Why should we change if something works fine? Actually, it was not working fine. The physicists found that is something wrong with this principle. Something wrong. And what was wrong? The wrong was the theory of electromagnetic waves, electromagnetism actually, which was to that time it was already developed and very good working everywhere. The theory it was made by Maxwell, so it was very good theory, very advanced, and it works very fine for electricity, for electromagnetic waves, radio propagation, whatever, lots and lots of other things. And interesting enough, it does not obey this theory does not obey this first principle of relativity. Instead was happening something like this. Like, for example, imagine that the electromagnetic waves, right? So electromagnetic waves are waves, right? Whatever kind of waves are they, but they are waves. So something is vibrating and spreading in space, right? So the waves is like, for example, we have waves here, right? Like on the ocean, and waves are going here like with a speed, some speed, or even going whatever. Waves are going to the shore, right? And imagine that you are trying to measure how often comes these peaks of these waves to you when you are moving here with the speed, like some speed here. So this is your frame of reference, right? Here we have one frame of reference, so some wave is going with some speed here, like for example, speed of light, like electromagnetic wave, right? And we are moving here, this way. What will happen? You might think first that probably the speed will be c plus v, right? So because we are coming together, right? So relative speed of the wave and us will be like c plus v. This is the first proposition. Actually, it follows from this first principle of relativity, Galileo's principle. Instead,
What is C? What is C?
C is speed of light.
Okay.
It's a fundamental constant. It's denoted by C all the time. Just good to know. So C. So instead was happening something else, and you can understand why. Because this is it is the wave. It's not an object, right? Like an object. It's not a man or whatever, right? This is a wave. And when the wave is moving, we see something interesting. When we try to measure what is going on, we will see that the faster we go in this way, the faster peaks will come to us. Like for example, if we're listening, if it's the wave of sound, right? This is the peaks of pressure, like air pressure, right? Which actually hit your ears here each time it comes to you. So here's hit 1, hit 2, hit 3, right? You understand? So now if you try to move here, it's easy to see that these hits will come faster and faster because you're just running this way, right? You are like flying over this, and this comes faster and faster to your ear. And if you go different way, not this but this, like for example with the speed of this wave, for example C or whatever, right? So instead of this thing may never come to your ear at all because it's like standing, right?
Yeah.
You are running from this wave. So the only thing what happens actually from your point of view will be something like this. If you're moving this way, it looks like they're coming very often to you. It's called frequency. So the frequency will be like this, very frequent, because it's coming like, right? Like for example, it goes tam, pam, pam, and you move fast this way. It comes ta 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 because you're moving very fast this way. And when we're moving in a different way, it will be even one, boom, and that's it, or even nothing at all. So waves behave differently. And electromagnetic waves, for example, behave the same way too. This effect. Where is the stress? Effect or effect? Effect. This effect is called actually Doppler. It is very well known. It is found by Doppler and calculated by the guy, I forgot his first name. The last name is Doppler. He was a physicist, and he found out the easy thing which you can hear actually when the train is coming to you. You see, it's like it's moving and then passing you. It's making the sound like "eeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeeee in this decrease when it passes you and goes away. So it's the same way okay, so this is called Doppler effect. So because of the moving you or moving the train, which is producing this wave. So it looks like that with waves something is very different. There's a Doppler effect, this kind of thing, and there's no something else with the speeds, right? So Einstein thought about this very carefully, especially on electromagnetic things, and he found out interesting thing. So because of this thing, there's a Doppler effect. He understood that, and actually it was measured already for the electromagnetic waves. So for light, for radio waves and whatever, it was already known for these waves. So he understood one thing, that the speed of light is constant. It never changes. It is fundamental constant. It never changes whatever you do. You run around, you move this way or other way, whatever way you go, the speed of light is still the same, and you know what the speed, right, is 300,000, right, kilometers per second, right? So this speed is fundamental. It never changes. And it's one of fundamental constants in physics. It's very, very stable and whatever. So this is constant. And if it's constant, it cannot be changed. If it cannot be changed, so you should change something with this adding or subtracting speeds, right? With this principle of relativity. In the new principle of relativity, he understood that should be whatever speed of your frame of reference, like you are moving, right? This way or other way, and if you're looking at this wave, right, the relative speed will be like c plus v, right? And interesting enough, it is equal to c. Whatever v is, whatever your speed is, it's still the same. That's what Albert Einstein realized, and the term is postulated, so make it a law. He said nothing changed. You're moving this way, c plus v. Moving different way is c minus v. It's still c again. So c never changes. Say yes.
The way that's possible is if v would be 0 every single time.
It's the same thing. No, v not 0. You know that you are moving, right? Like you know that you are like, I'm walking. I know that I'm walking. All around is moving relative to me, right? I'm moving this way. Everything else moving the opposite way, right? If I move, you see, right? Like when I'm moving, the whiteboard moving opposite to my direction of movement, right? So moving this, my hand moving this way, desk moving other way, and the same opposite.
No, but the point that Viti is making is that if you look at that equation, c plus v equals c, when you solve for v, the only answer is v equals 0.
Yes, but it means only one thing, that physics is not mathematics. The physics is something different. So it is said that the speeds close to the speed of light are not additive. So they are not additive like numbers. When this thing 1 plus 1 is not equal to, not equal. 1 plus 1, yes, it's like 1 plus 1, like c plus c, right? The same as 1 plus 1, right? It will be c. Again.
1 plus 1 no longer equals 2.
So you may move with the speed of light too. You may move and look at this wave of the light.
So he's proving that nothing can go faster than the speed of light.
Yes, it's not about even faster or slower. Actually, it is about fundamental constant of speed of light. Speed of light is fundamental. It's not changed. The term is, mathematical term is, it is invariant. So not variant, not variative, invariant. It's totally invariant in all frames. Whatever you do, the speed of light does not change. And this is, of course, it's very paradoxical. It's caused a lot of questions, and lots of people don't understand how can this be. And of course, it's not obey like simple rules of mathematics. There are mathematics to it, yes, but it's not that, not just plus. There's something else, some other transformation mathematical formula which gives you relative speed. So for relative speed, you should not write this c plus v. It's not even correct mathematically to write it like this. You should not do it. We are trying because we are moving from this, we're looking from this point of view, but this point of view is wrong. So there is no addition of this. We should not add 1 plus or 1 minus or subtract. So this is very, very paradoxical concept, and actually it is called special relativity. Special principle of relativity. Special relativity principle, right? But you see, it's not even about relativity. It is about relativity because speaking about this, right? But it looks like more that it's about absoluteness. The C is absolute. It is constant. It never changes. So it's absolute in all frames of reference. So this is a very important thing. We will talk about this like a lot later, about this and this. Now just think about this. But Einstein, he didn't stop on that. he was really thinking type of guy. So he started thinking that maybe this principle of relativity, that kind of principle, can be spread like to the more others, to the other fields of physics. It may be generalized. And in 1916, the same guy, Albert Einstein, came to another principle, which he called principle of general relativity. So that was special, right? Here was special. And here is general principle of relativity. And in this principle of relativity, he thought not about speed, but he thought about acceleration. Remember, right? Acceleration is a change of speed. How much speed is changed per second?
What?
Huh?
I'm sorry. Never mind. I'm sorry.
Yeah. So, what was his way of thinking? Like, imagine that you are sitting. Imagine that you are sitting in the elevator, right? In the elevator, which is held by some rope, right? Somewhere there. And you are standing there, not sitting, standing there. And of course, there is we talk about this, there is an acceleration of the Earth gravitation, g, right? Which is 9.8 meters second square, right? When the rope is when the rope is okay, you're just standing there, right? And you have your weight, right? You have your weight. So some force, which is called gravitational force, it push you to the floor of the elevator, right? And so this is force of gravity, right? Fg, and the force of the floor. Remember this third law of response and push and response.
Equals reaction.
Yeah. What's it? Say it again. The words.
Action equals reaction.
Action, reaction. Yes. And the reaction of the floor is equal actually to this, right? To the force of gravity, and it holds you standing. It does not allow you to fall down. It holds you, right? So these forces are equalized, and you're not falling. You're not going anywhere, right? Now, what he thought? Let's break this rope. What will happen? What do you think will happen?
That you never breaks.
Free fall.
There's still force of gravity, right?
Free fall.
Did a free fall.
Free fall, yes. There is still force of gravity, but it is equal to you and to the elevator, right? The same force. You both begin falling down with the same speed, increasing speed with this acceleration. So your speed will increase, right? Each second will increase 9.8 meters per second. And the same thing will happen with the elevator itself. So what will happen actually? The floor may be here and you may be here. And you are falling with the same speeds. You and the elevator. And the same accelerations. No, G here and G here, right? So nothing will change relatively for you, between you and the elevator. Everything will be the same, but you will be falling, and the elevator will be falling. So what you would feel here, what do you think? I think you know, but think what you will feel here.
Free fall.
Free fall.
You feel weightless.
Right, you will fly, or actually in this elevator, because the elevator is falling with the same speed and same acceleration as you. So from this simple thought experiment, it says thought experiment, he never fell down in the elevator, of course, right? He will be dead by now. So to that moment, he made this thought experiment. He understood that he will be weightless he'll be feeling weightlessness in this case. And what he think? He said that actually locally, so in small spaces, force of gravity is equivalent to acceleration. So he said that force of gravity actually is the same thing as acceleration. Another way,
Who said that?
Einstein. So another way, you may feel like in different, like for example, here is the star, right? Gravitation, with the gravity, right? So it makes the space-time around, it changes in a certain way, which makes you, if you are around somewhere, like which makes you fall here with different accelerations in different places. So here is maybe acceleration 1, here is acceleration 2, here acceleration 3, here acceleration 4, here is 7, whatever. In different points of space-time you have different accelerations. And this is called field. This lots of vectors. You see, these all vectors, right? These arrows, right? So this field of arrows, it is called field. So he said that the field of gravity is actually the field of acceleration. That's it. And this acceleration may be interpreted as a space-time curvature. So he comes to the curved space-time. Curved space-time. And this concept he finished in 1916. He thought about it since maybe 05, so like 10 years he was thinking of it, and then he comes to mathematical theory of curved space-times. And the idea of curved space-time is exactly that in each point of space-time you have different acceleration. And it's actually because it's called curvature, so he actually made equivalent or equal the field of gravity and the accelerations, so curvature of space-times. This is called, this thing, I would not like put it in words, but this total concept is called actually general principle of relativity. General principle of relativity.
But I don't understand the use of terminology curved space. Why is it curved?
It is called because this. Remember, we spoke about small piece of room of space inside the elevator, right? Of course, Einstein knew, right? He knew from the law of gravitation, which was found by Isaac Newton, right? He knew the law of gravity. Like, and the law of gravity says that the force of gravity actually decreases with the distance from the gravity, the center of gravity, like for the star, like our sun or whatever, and decrease by inverse square of distance, right? So if you, that was the law. Remember, actually I wrote it to you. Two masses, mass of star, u mass, right, and divided by distance squared, radius distance. This is the force of gravity. So he knew that, of course, because he was a physicist, right? So he knew that it depends upon distance. So in different places, force is different, and because force is different, acceleration is different. And just he make it totally opposite, right? He put everything to look to everything from a different point of view, and he said, okay, we will not talk about forces. There's no forces at all. Actually, interesting enough that the theory of relativity is so-called forceless theory. No force, no forces here. There are lots of forces in Newton theory, but there are no forces in Albert Einstein theory.
Without forces, then there's no acceleration.
Right. That's I'm coming to the question, right? So.
Wait. We're doing questions?
No. The question that your dad asked, right? So I'm coming to to show you what is going on. So what they mean under forceless, right? Force in the previous theory, the force actually makes, like, without force you're moving straight, right, with a constant speed. But if something force is applied, your trajectory is moving like this, right? So it's curved, right? So what Einstein said, that okay, there's no force, but some trajectories can be curved by themselves. How can it be?
Like light can bend.
No, just they can bend, yes, they maybe bend, right, by themselves. But how can this be? With no force, right? What can change this thing? He said, okay, it can be in curved spaces, because the curved space is, like, for example, let's like curved space, like, for example, the globe, right? You imagine the globe. It's a curved space, two-dimensional space, the sphere. And you see, if you try to make a shortest line here, like something is moving using the shortest way, like what this is the shortest way on the globe when measuring on the globe, right? We're measuring on the surface. This is the shortest way from point A to point B. Will be like this, right?
Oh, that's why it's curved.
And this is curved because the globe, the surface of globe is curved, right? So that's why it's curved. So, and this shortest path, it is called geodesic. Geodesic. I think we will mention it sometime long ago. So geodesic is the shortest in the curved space. So what Einstein did, he actually used the mathematics of curved spaces, the actually four-dimensional curved spaces, into this thing. And then you see there's a shortest thing. There's no straight lines in the curved space. There's no straight lines. This line is not straight, right? It may be shortest, but it's not straight. You see, it's curved. So there's no shortest paths, but or lines, but still they're short, right? So you can talk about geodesic or the shortest lines, but you cannot talk about not curved lines. So that's what he did. He used this mathematical approach of curved spaces and applied it to the gravity, and actually he found the new equations, which are more general than Newton's equations. They were tested experimentally many times in different ways. They actually they meet all the experiments, everything fine. So now it is official physical theory, like since 1916, something like this.
But a quick question.
Yes.
Forceless. When you say forceless, it only applies to gravity. There is no force of gravity.
Yes. Yes. But when this term, right, it applied to gravity. But actually, in modern physics, all other forces are forceless too, because in modern physics, it's a very little ahead. But actually, we're talking about we live in parallel. Like parallel spaces, parallel space-times. There are many curved spaces which are combined here together. And actually, many of them, like many fields applied to one place. There will be electromagnetic force, electromagnetic field, right? Then can be gravitational field, right? There are also nuclear fields and nuclear forces, right? And then can be applied to the same particle. Like, for example, the same thing here they use mathematical. They use many spaces times, like in each and one point. So here are many spaces, not only one, but there is another space here and another, and they are all applied to any particle. There are many together. It's that kind of mathematics. And this is actually what we have right now in physics. So we have many parallel space-times which are applied to different objects, and they're all forceless because it's all about curved spaces, curved spaces. So each time object chooses the shortest path, but the shortest path can be seen in different way. Okay. So we are not. I think the time is out. So any questions to this?
No.
Huh?
No, no.
No, thank you.
Okay. So I'll ask you. Okay. So, okay, are you ready to write? Huh?
Almost. Oh wow, we spoke
Okay.
exactly 40 minutes.
Yeah, hold on.
Okay, I'm ready.
Okay. So the first question is, imagine. So when we talk about, remember, it's all about frames of reference, and then relative things. Like imagine how a world look like if your height, right, is increased like tenfold and then hundredfold. How the world would look like in this case. Just imagine, think about it, compare yourself with other things and everything like this. Also then do the same with your width.
How the world look if you were
And
back?
think carefully what will happen actually with the world and how you would fit in this world, whatever. Okay, you got the idea? But think carefully because I think it's pretty intriguing. Okay, the second question is, imagine the world. Again, this is a frame of reference. We will continue. It's not probably principle of relativity. This is a number like A maybe, because we will continue. This is not finished yet. It's not the end of the principles, unfortunately. Or maybe fortunately. So the second question: imagine the world around you, right? If you can see or visualize, right? You can see, visualize, or hear. So the first is see and visualize, and another is hear. So two, like smells in this world.
Are you writing it down?
Visualize. If you can
see and visualize.
visualize or hear smells, then genes around, like genes in humans.
Like
whatever.
genetics?
Yeah, for example, not genetics, but genes, right? How you can, and the third is the same thing: view or see emotions, not on the faces, but directly.
This is exactly like the weight in the second question.
Directly.
Okay. You can see emotions when somebody's happy.
Yes, you can see it on the face, so you can imagine further, right? You can imagine further and think how you will see it like directly. See directly through people, right? Okay, so you got the question, right? And now the third question is, imagine or design, I don't know what is the best word for this, the craziest examples of changing reference frames. Because the previous two, actually, they were about reference frames. There's something, let's change your point of view to the world, right? At the world.
So how can you change your point of view of the world?
Yes, how? But try to find out the craziest, like the very, very interesting. Okay, something like this. 3, and you'll tell them to me next time. Okay?
So I'm a planet and I have life living on me.
You want what?
It should also have hair.
Okay, no mean imagination. Okay, good, nice. But okay, it's up to you. Okay, guys, that's it.
These questions are really interesting. Yeah, like they're more philosophical.
Okay, we'll continue a little. So because these principles are very important, so we'll talk about them later, and then we'll continue to more detailed things. Okay. So any more questions on this?
No, nothing. This is
Nothing.
really interesting. Bye, good.
Okay. So see you guys.